Hi everyone. Today is the maths. Okay, so you'll have a webinar on maths. So David Vaccaro is going to be the host today. I'm moving house, so I am literally all covered in dust. So I can't do the webinar today, but next week I'll do a webinar from my new place. Hi, David. David is coming. Just a minute or so. Can people hear me?
Yeah.
Okay, good. David's about to join, just technical difficulties. Please don't leave. Right, David is here. David, you're the host now.
Super. Thank you,
Yeah.
Ivan.
Sorry, I'm literally covered in sawdust, so I'm in the process of moving.
Yeah, you're moving house, aren't you?
Yes.
Right, well, I'll let you get back to your sort of electric screwdriver and your sort of boxes.
Jigsaw.
Yeah, right. So we've got coordinate geometry, everybody. Right, sorry, I'm just pulling up the sheet. If you could just, as I just pull up the sheet, if you could just let me know any particular topics that you're keen to go over, because I won't be able to do every sheet question on the sheet, or if there's a particular question number you'd like to do, then let me know in the chat. Otherwise, I will get started. Oh, a minute. So from the chat, question number 7. Okay, well, I'll start on a slightly earlier question just to get myself warmed up, but I'll make sure that I include question 7 on the way through. Right. I don't know, my video is playing up, so you might not be able to see me, but I'm just going to turn on the light. So let's have a look at problem number 1. That's as good a place to start as any. So it says, find the equation of the line passing through the point 152 and crossing the x-axis. That's strange that there's a triple. I suspect that that's not meant to be 3 dimensions. So it says crossing the x-axis at 45 degrees if measured clockwise from that axis. So clockwise would be round this way. So from a mathematician's point of view, that's minus 45 degrees. So we can see straight away that the gradient is going to be negative. And because it's 45 degrees, the tangent of 45 degrees is 1. So the opposite and the adjacent would both be 1. So the gradient is negative 1. Just as an aside, it's worth noting that in general, the gradient of a line is the tangent of the angle that that line makes with the axis. So the gradient is negative 1. So y equals negative x plus c. And I'm going to make the executive decision that it passes through negative 1, 5. So when y is 5, x is negative 1. So we get 5 equals 1 plus c. So c is equal to 4. So the equation is 4 subtract x. Okay, let's move on to a later example. This is quite... So this is actually one of the worked examples. But this is from a... So this is... I'm going to have a look at example number 4. So it says, show that the points A, negative 5, 4, B, -1, 2, and C, 5, 2 lie at 3 corners of a square, find the coordinates of the fourth corner and the area of the square. So I'm going to tweak this slightly, and I'm just going to give 2 points. So I'm going to do example 4-. So I'm going to say that A, and I'm just going to make up some points, 2, 8, and C, I'll do 10, 2 are opposite corners of a square. A, B, C, D. Find the points B and C. So we've got A is 2, 8. C is over here, is 10, 2. And then we've got I've drawn it a little bit badly, but we've got points B and D. So this is clearly a more difficult question than the previous one, because the previous question gave me 3 points, whereas this one has only given me 4 points. Has only given me 2 points. Now, let's see how we could do this. Now, I'm going to take a particularly geometric approach to doing this question. So the first thing I'm going to do is I'm going to draw the line AC. And this point here, M, which is the midpoint of AC, which is going to be the point 6, 5. So 6, 5 is the center of the square. Now, especially if you're watching this on the webinar, it'd be quite nice probably to sort of pause the video at this point and think about how to do the question. And one thing for sure you could do is you could find the equation of the line through M, which was perpendicular to AC. So you could find the gradient AC and draw a perpendicular. And then you could look at the equation of a circle with center M and radius MA, and recognize that that circle would meet this perpendicular line at B and D. Okay, and I'll leave that long calculation as something of an exercise. But let's think of a slightly different way of doing this problem, which is much more geometric in nature. So the vector I can find is I can find the vector MA. So the vector MA is -4, 3. Okay, because we've gone 4 units to the left and 3 units up. Okay, so we've got this vector, -4, 3. Now, to get the vector MD, we need to rotate by 90 degrees. Okay, now if I rotate this vector -4, 3, and I rotate it by 90 degrees, I end up going 4 units up and 3 across. So I can write that the vector MD is 3, 4. And so the coordinates of D, so OD, is OM plus MD. We know the position vector of M, it's 6, 5. MD is 3, 4, so we get that D is 9, 9. We then just need to rotate by 90 degrees again. So this vector 4, 3, when I rotate by 90 degrees, becomes 4, negative 3. So I can write down that MC is 4, negative 3, which just gives me that OC is 10, 2, and I knew that. And then I just complete the picture by rotating another 90 degrees. And so that would take me 4 down and now 3 to the left. So my vector MB is negative 3, negative 4. So the position vector of B would be 6, 5 plus negative 3, negative 4, which is then 3, 1. So this point D is 9, 9. And this point B is 3, 1. Okay, and the idea for this question, so the idea for that question is you could avoid a lot of coordinate geometry just by thinking how a vector rotates round 4 right angles. Okay. I just want to double check people are happy with that example. If so, just put a thumbs up in the chat to say that you're happy. If not, put any questions that you might have now before I continue looking at some more questions. Excellent, lots of thumbs up, which is nice. Okay, I'm now going to look at problem number 7, which people asked me to look at. And so it says, determine the area inside the circle defined by x squared plus y squared minus 8x plus 4y plus 4 equals 0, but outside the triangle bounded by y equals x minus 7, y equals 1/5, 2x minus 29, x equals 7. So let's start by writing down the equation of the circle. So I've got x squared minus 8x. I'm going to leave a little gap, you'll see why. Y squared minus 4y is equal, I'll take the negative 4 over. And now the reason I've left a gap is I want to complete the square. So if I add 16 here, I end up with x minus 4 squared. And if I add 4 here, I end up with y minus 2 squared. So I get x minus 4 squared plus y minus 2 squared equals 16, which tells me that the center of the circle is at 4, 2. The radius of the circle is 4. Okay, so this is my circle, and notice that it goes through the point 0, 2. Oh, wait a minute. Sorry, this is plus 4. So it goes, sorry, the center of the circle is 4, negative 2. And it goes through the point 0, negative 2. And this is going to be the point 8, negative 2. And this is going to be the point 4, 2. Okay, let's now start thinking about the lines that they've given me. So one of the lines is x equals 7. Okay, so I can draw the line. I can draw the line x equals 7. I can also find the coordinates of the points of intersection. So when x equals 7, we've got 7 minus 4 squared plus y plus 2 squared is equal to 16. So this is 9 plus y plus 2 squared is equal to 16. So y plus 2 squared is equal to 7. So y equals -2 plus or minus square root of 7. Square root of 7 is bigger than 2. So we've got these 2 points. We've got these 2 points here and here. Okay, we then need to look at the line y equals x subtract 7 and look at where that meets the circle. So if I put y equals x subtract 7, I get x subtract 4 squared plus x subtract 5 squared is equal to 16. So I get x squared minus 8x plus 16 plus x squared minus 10x plus 25 is equal to 16. The 16s cancel. So I get 2x squared minus 18x plus 25 is equal to 0. And then I can solve that. I can solve that quadratic. Which is not an especially nice quadratic. Okay. I'm just interested where it meets the line x equals 7. So it meets the line x equals 7 here at 7, 0. So we've got and when x equals 4, that line is -3, so the center is up here. 4, -2. And then we've got the third line. Y equals 1/5 2x subtract 29. So this is 0, -7. And then we've got -29/5. So that's -29/5. And then we've got a gradient of -0.5. Okay, so we should probably find the points where that meets the other 2 lines. So we've got this triangle. Okay, so let's see where it meets the line y equals x subtract 7. So we've got x subtract 7 is equal to 2/5 x minus 29/5. So we get 3/5 x is equal to 6/5. So x is equal to 2 and y is equal to -5. So we've got this point here is 2, -5. And then this other point, where it hits the line x equals 7, we've got y equals 1/5 of 14 take away 29. So that's y equals -3. So this point here is 7, -3. Okay, so what we've got is the lines meet at 2, -5, 7, -3, and 7, 0. Now, what I'm going to do is I'm going to check whether these points are inside or outside of the circle. Okay, so if we consider x minus 4 squared plus y plus 2 squared at each of these points, we get, for the first one, -2 squared plus -3 squared. So that's 4 plus 9, that's 13, and that's less than 16. For the second one, we get 3 squared plus -1 squared, which is 10, which is less than 16. And then for the last one, we get 3 squared plus 2 squared, which is 9, which is again 13, and that is less than 16. So what I've just verified here is that A, B, and C all lie inside the circle. Okay, which makes life considerably easier because I just need to find the area of the whole circle and then take away the area of the triangle. Okay, now if I look at the triangle, the natural side to consider as being the base is this vertical line here, and the difference in the y coordinates is the difference from -3 to 0. So this is 3, and the height is then the difference in the x coordinate. So that's a difference between 2 and 7. So that's 5. So the area of the triangle is 3 times 5 over 2, and that's just half base times height. Okay, and then the area of the circle is pi r squared, but we can read off the radius of the circle from the Cartesian equation. So in x minus 4 squared plus y plus 2 squared equals 16, this 16 is equal to the radius squared, so the radius is equal to 4. So the area of the circle is 16 pi, and then subtracting the area of the triangle gives 16 pi take away 15 over 2. Okay, so yeah, quite a tricky question, that one. The thing which came to our aid is that the triangle lied entirely inside of the circle. If it hadn't been entirely inside of the circle, we would have needed to do a little bit more geometry. So I'll just go back to the Zoom meeting. Is everybody happy? Is everybody happy with that solution to question 7? Or does anyone have any questions? Looking at the chat, yes, people have just correct. Thank you, Alfie. Alfie corrected me with the +4y. I managed to correct myself. But are people happy with the answer to question 7? If so, put a thumbs up in the chat. Excellent. Lots of thumbs up. So I think we're ready to continue. And the next question people requested was question number 11. Oh. I'm a little bit scared because I've seen COMPOS questions with 1 star. I've never seen a COMPOS question with 2 stars on it before. This could go well, or this could go badly. So, question number 11. The base AC of an isosceles triangle ABC is a chord of a circle of radius 1 both A and C on the circumference. So sorry, AC is the base. And A and C lie on some circle. Whose center is located inside the triangle. Looks a bit better. Two tangents to the circle pass through the point B, where the points of the tangents are denoted as D and E. Okay, so we've got tangents going through B at D and E. And the radius of the circle is 1. So we've got 1, 1, 1. Find the area of the triangle DBE if AB equals BC equals 2 and angle ABC is equal to 2 arc sine 1 over root 5. Okay, so let's just use what we know. So AB is 2. Angle ABC is 2 arc sine 1 over root 5. So this angle here, theta, which is the sort of semi-vertical angle at B, so theta is equal to arc sine 1 over root 5. And we need to find the area of the triangle DBE. Okay, so theta is arc sine 1 over root 5. So if I let M be the midpoint of AC, AM over AB is the opposite over the hypotenuse, and that's equal to sine of theta, so that's 1 over root 5. So AM is 2 over root 5. And then the other length I can find is BM. And I can do that by Pythagoras. That's the square root of the hypotenuse squared, which is 4, minus AM squared, which is 4 over 5. So that is the square root of 1 over 5. So that's 1 over root 5. So I've got 2 over root 5, and I've got 1 over root 5 for the height of my isosceles triangle. Okay, the next distance I can find is I can find the distance from M to the center of the circle, O. So if I now consider the triangle AMO, so AM I've just found is 2 over root 5. AO is the radius of the circle. So AO is 1. And then by Pythagoras, oh, wait a minute, I've made a mistake up here for my BM. My BM is 4 minus 4/5, which is square root 16 over 5. So that's 4 over root 5. So BM is 4 over root 5. Now by Pythagoras, I can find that OM is the square root of 1 minus 2 over root 5 squared. So OM is the square root of 1 minus 4/5. So that's the square root of 1/5. So that's 1 over root 5. Okay, so if I just return to my diagram, I've got AC, and I've got the midpoint M. AM is 2 over root 5. MO is 1 over root 5. And then OB is 3 over root 5. But if I now consider the triangle OBD, so I've got OD so if I consider the triangle ODB, I've got some important things. So firstly, ODB is a right angle because DB is a tangent. So angle ODB is 90 degrees. OD is 1. So now I can use, I can now use Pythagoras. So I've got DBO. This is 1. So I've got B. OD is 1. OB is 3 root 5. This is my right angle. So DB by Pythagoras is the square root of 9 over 5 minus 1, which is the square root of 4 over 5, which is 2 which is 2 over root 5. Okay, now by symmetry, so I've got this nice triangle, DBO, which I'm just going to redraw as a right angle triangle. So BDO is, DO is 1, DB is 2 over root 5, and OB is 3 over root 5. And so what I can find is I can find the sine of this angle OBD. So the sine of OBD is the opposite over the hypotenuse, so that's root 5 over 3. Okay, so if I now just collate everything, I've got BD is 2 over root 5. By symmetry, BE is also 2 over root 5. And I've got this angle here, sine of OBD. So this angle I'll call phi. I've got that sine phi is root 5 over 3. Okay, because it just carries on down to O, where O is the center of the circle, but I'm just stopping at the point where I make the triangle OBD. Now what it wants is it wants the area of the triangle DBE. And now we're very close to getting there, because I know the sine of phi, so I can find this angle which takes me to the midpoint. I'll call that n. So dn is equal to sine phi times 2 over root 5. So that's root 5 over 3 times 2 over root 5, which is equal to 2/3. So dn is 2/3. Ne is also 2/3. And then the last thing I can do is I can find the height, NB, by Pythagoras. So NB is the square root of the hypotenuse squared. So that's 2 over root 5 squared. So that's 4 over 5. Minus 2/3 squared. So that's minus 4 over 9. Which is 36 minus 20. So that's 16 over 45. So that's 4 over root 45. And now the area is 1/2 base times height. So this is the area of DEB. The base of the triangle is 2 lots of 2/3. So that's 4/3. The height of the triangle is 4 over root 45. So that's 16 over 6 root 45. Or 8 over 3 root 45. Okay, so I wonder if there's more elegant ways, to do it. But that certainly seems one way to do repeated use of Pythagoras to get the height of the original triangle AB, to get the height MO, to then get the difference in heights, then to use Pythagoras on this triangle to find DB, and also to find this semi-vertical angle, and then having found the length of DB and the length of DE, to find the height, and then from the height to find the area. Okay. I would need to think about it to see if there's a nicer way of doing it. I'd also need to double check that I haven't made any arithmetical errors along the way, but this is certainly a method that would work. Let's see if the troops are happy. Okay. Does anyone, if you think that I've got the right answer to question 11, or if you're happy with what I did to question 11, put a thumbs up into the chat. If not, either let me know of any corrections that I need to make or any questions that you might have about question 11. Lots of thumbs up, excellent. Let's keep going. Okay, I'm going to make up a problem of my own. So the first thing I'm going to do is I'm going to draw a triangle. And the next thing I'm going to do is I'm going to draw a circle inside that triangle, so what we call an incircle. And I'm going to label some points. I'm going to put A, B, C, and I'm going to call the 3 points of intersection P, Q, R. And so my first question is to find AP, BQ, and CR. Okay, in terms of A, B, and C. Okay, and I'm just going to label the triangle normally, where A is the side length opposite A, B is the side length opposite B, and C is the side length opposite C. So A is equal to BC, B is equal to AC, and C is equal to AB. So that's going to be my first part. And then my second part is going to say, find the area of the triangle in terms of A, B, C, and the in radius and R. Okay. So if you're watching this on the webinar, pause the video at this point. If you're watching this live, try and think about these. Questions. So let's try and find AP, BQ, and CR. So firstly, I can note that AP is equal to AR. Is equal to AR because they are tangents to the same circle. Similarly, I can say that BP is equal to BQ for the same reason. And I can say that CQ is equal to CR, again for the same reason. Now, if I add AP plus BP, or I'll say AP plus BQ plus CR, What I've done is I've added one of the greens, one of the yellows, one of the blues. And so that's exactly half of the perimeter of the triangle. So AP plus BQ plus CR is the perimeter of the triangle, which is A plus B plus C, all over 2. And I'm just going to color code this for a moment. So what I've done here is I've added a green. So I've added a green AP, a yellow BQ, and a blue CR. But let's say I wanted to find AP. If I look at my BQ plus CR, I've just taken this final side length, I've just taken A. So I can write that AP is equal, sorry, AP plus A is equal to A plus B plus C over 2. So AP, and it's worth giving this a name. I'm going to call A plus B plus C over 2 the semi-perimeter. So I'm going to write it as S. So AP is S minus A. And now by exactly the same reasoning, okay, I can say that BP or BQ is going to be S minus B, and I can say that CR is S minus C. Okay, let's just sort of check that the machinery is working. If I add S minus A plus S minus B, which is what I think AP plus BQ should equal, I end up with 2 lots of the semi-perimeter minus A minus B, but 2 lots of the semi-perimeter is just the perimeter, A plus B plus C. Then I subtract A and B, and so I just get left with C. But that's exactly what I should get if I add AP, which is this length, and BC, which is this length. I should just get the length of AB. Okay, so the machinery is working. So for the first question here about my in circles, AP is S minus A, BQ is S minus B, CR is S minus C. Okay, next question. Find the area of the triangle in terms of A, B, C, and R. So let's imagine my triangle. Then I've drawn my in circle. And I've got my in radius R. One of the first things I can do is I can find the area of this triangle, which is the area sitting on the in center and the side C. So this shaded area is 1/2 base times height. So the base is C, the height is R. So this shaded area here is 1/2 C. But then I can play the same game on the other sides. So this shaded area sitting on the side B is 1/2 BC. And this shaded area over here is 1/2 AC. So the total area of the triangle is 1/2 AC plus, sorry, 1/2 AR plus 1/2 BR plus 1/2 CR. Because in each case, and I think I might have said it wrong, in each case, the height of the triangle is the in radius R. Okay, because these sides are all radiuses, sorry, are all tangents to the circle, so they're perpendicular. So the area of the triangle is 1/2 A plus B plus C R, but 1/2 A plus B plus C is just my semi-perimeter times R. So the area of the triangle is RS. Okay, so what I've done there is I've found the lengths of the sections of each length that take me up to the in circle, and I found all of them in terms of the semi-perimeter S. I've also found the area of the triangle in terms of the semi-perimeter S. Okay, I'm just going to go back to the chat, and I'm going to ask people if anyone's got any questions about that calculation. If you're happy with that calculation, put a thumbs up. If you're not happy with that calculation, then put a question into the chat. Okay, I'm going to ask another question, and this is not a leading question in any direction at all. Who liked that calculation and would like to do something similar, taking that result a little bit further? So if you'd like to see something a little bit more based on like the in circle and the little bit of geometry that I've just done there, say yes. If you'd like to do something different, then put that you'd like to do something different into the chat. Okay, so we've got yeses. Okay, so what I'm going to do now, so I'm going to draw a triangle. And this is a little bit tricky to draw. So I'm going to label the corners the same way. So this is A, B, and C. Okay, and what I'm going to do now is I'm not going to draw a circle inside the triangle. Actually, I'm going to just give myself a little bit more space. So I'm going to draw A, B, and C. I'm going to draw a circle that lies, and it's a little bit hard to draw. Outside of the triangle and touches these three these three sides. Okay, I'm going to call this the X circle. Okay, just to convince you that this is possible, what I could do is I could well, these two distances are the same because they lie on the same circle, and then this distance is the same because these two, well, I can draw the X circle for the similar reasons I can draw the in circle, is that I could bisect this angle, and where they meet, I could make a point, and then that point is going to be equidistant from these two lines by symmetry, and then it's also going to be equidistant from these two lines. And so that means that this distance and this distance are the same, this distance and this distance are the same, so the three distances are the same. So the X circle can touch the triangle on the outside. Okay, let's now try and do a similar game. So I'm going to call these points, I just need 3 consecutive letters. I'm going to call them S, T, and U. Okay, so let's try and find these distances. So the first thing I can say is that SB is equal to BT because they are tangents from the same point. And then I can also say that CT and CU are the same distance because they are tangents at the same point. And then the other distance which are the same is AU and AS. And so these are tangents. These are all tangents from the same point. Okay. Now, what I know is I know that SB, so AS, which is my blue length, minus SB, which is my yellow length, is equal to what I've called C before. Okay, because if I take this yellow length away from the blue length, I'm left with the line AB. I can do a similar thing with the green length, and I can say that AS minus CU, so that's my blue minus my green, that is equal to B, and that is equal to AC. Okay, and then the other thing that I can do is I can say that my yellow length, which is SB, plus my green length, which is CU, okay, if I add my green and my yellow, I make A. Okay, because that's a green and a yellow length together makes BC. So let's add all of these three equations. So I'll call them 1, 2, and 3. If I do 1 plus 2 plus 3, I get 2 lots of AS minus SB minus CU plus SB plus CU. So those all cancel, is equal to A plus B plus C. So AS is A plus B plus C over 2, which is equal to S. Okay, so my semi-perimeter. So this long blue length is equal to S, and then my little length BS is AS minus C, so that's A plus B, well, that's S minus C. And my length CT, or CU, is AU minus B, so that's S minus B. Oops. So if I just take my diagram that I had before, with my in circle, if I want to extend it to my X circle, then the X circle, the total distance from the point of contact from the X circle from A is the semi-perimeter. So I've got an extra blue length here, or I've got an extra yellow length here. So this is it's my X circle, and this is my S T U. Okay, this is my X radius, I'll call it capital R. This is my X radius, I'll call it capital R. Okay, I'm aware that I've done quite a little bit of geometry there. But can I just double check that people are happy with me so far? Can people just put a thumbs up if they're happy with the geometry that we've got to at this point? There's a thumbs up there. Okay, now where is this all going? Okay, well, what I would like to do is I would like to try and use this geometry to get a formula for the in circle of the triangle. So I want to find, my goal is to find little r. And the reason I would like to find little r is that I know that because the area of the triangle is RS, if I find little r, that would tell me the area of the triangle. And what I'd like to do is I'd like to find little r in terms of A, B, and C. Okay. So I'm going to find little r by finding various similar triangles. So the first thing I will note is that I can look at the triangles APR and then my incircle, the center of my incircle, I. Okay, so AP is S minus A, AP is S minus A. These two triangles, these two in radiuses are R. So what I've got here is a pair of two congruent triangles. Sorry, two congruent triangles. So this angle in here is A over 2. Okay, because the triangle API and the triangle ARI have just got the same 3 lengths. So they've got the same angle, so the angle splits in half. But I can make exactly the same observation about the larger triangle AU and then my capital R and AS and my capital R. So AS and AU are both equal to the semi-perimeter S. The X radius is capital R and the two triangles are the same. So ASR is congruent to AUR, and so this angle is A over 2. So because I've got two similar triangles, I can say that the sine of angle A over 2 on the one hand is R over S minus A, but on the other hand, it's R over S. So my little in radius here is R times S minus A over S. Okay. But the only problem I've got is I don't know an expression for capital R. But I can do something else. Okay. I can look at this triangle. BPI, so that's this triangle here, and by exactly the same argument that bisects the angle B, so this angle here is B over 2, and BP is got length S minus B, and PI is R. But I can now find that this angle over here, CBS, so this angle in here is 180 degrees minus B. If I then consider this line to the center of the X circle, that bisects this angle. So this angle in here is 90 minus B over 2. So this angle at the center of my circle is B over 2. So this triangle here, BS, and I'll call it J, the center of my X circle. This is B over 2. And so we've got R, and then this blue length here is S minus C. So basically what I've done there, and I'll just highlight them, is I've shown that this triangle in here, which uses the incircle, is similar to this triangle, this right angle triangle out here that uses the X circle. So I can now get two expressions for sine of B over 2. On the one hand, sorry, not sine of B over 2, tan of B over 2. And this one, sorry, this is also not a sine, this is a tan. So tan of b over 2 on the one hand is r over s minus a. Sorry, s minus b. Notice that just follows by symmetry because it's the equivalent expression replacing an a for a b. So we would be surprised if tan b over 2 did not equal r over s minus b. But the expression for the incircle, the tangent of this angle uses the opposite as s minus c, and then the adjacent as capital R. So this is a different style of expression, and it tells me that my x radius r is s minus b, s minus c, all over r. I can now substitute that into here. And so I get r is equal to s minus a, s minus b, s minus c over sr. And so I get r squared is equal to s minus a, s minus b, s minus c, all over s. Just as a little sanity check, dimensionally, this is correct because all of these three quantities on the top, the s minus a, the s minus b, and the s minus c, their lengths measured in meters. The s, which is the semi-perimeter, is also a length measured in meters. So overall, we've got a length squared. As well as being dimensionally correct, notice that if I swap the a, the b, and the c round, I would still get an expression. I would still get the same expression. And of course, the in radius shouldn't depend on which side I call A, which side I call B, which side I call C. So I'm happy that this is a symmetric expression. So if I square root this, I get an expression for the in radius. I can also get an expression for the area because I know that the area is the in radius, which is my little r, times s. So my area squared would be r squared times s squared. And if I times both sides of this expression by s squared, I get s times s minus a, s minus b, s minus c. So I get this lovely result that the area of the triangle is the square root of this expression. And so if you've never seen this before, this is an expression for the area of a triangle in terms of the side lengths. There's very many different proofs of this result. This is one of my favorite. So this is using the in circle and the X circle. But this result has got a name. If you think you know the name, put it into the chat. But this is named after a Greek mathematician called Heron. So this is called Heron's formula. Okay. If you like that and are happy, put a thumbs up in the chat. If you've got any questions about the proof, then put the questions into the chat at this point as well. Excellent. Yeah, Amanda's recognized it as Heron's formula. Lots of thumbs up. I hope that's lots of thumbs up, liking that lovely bit of geometry. Okay, and so that's quite a heavy-duty geometry, but that's lots of bisected angles, similar triangles, and it turns out that in sort of like Olympiad problem solving, for example, this decomposition of the triangle into these three lengths is also useful. Just as an aside for Heron's formula, we shouldn't be too surprised by the S minus A, S minus B, and S minus C, because if I want to draw a very silly triangle that is otherwise known as a straight line, then one of the sides is exactly half of the perimeter. So if one of the sides is equal to the semi-perimeter, then A is equal to 0. So I shouldn't be at all surprised by these three brackets. So yeah, so it shouldn't be, that shouldn't be a surprise. We need a fourth term in the formula in order to make it dimensionally correct. But then the fourth term in the formula needs to be symmetric in A, B, and C. And pretty much the only symmetric expression you can write down using the lengths A, B, and C is A plus B plus C multiplied by some constant. So the area squared, the formula almost has to be of this form, because it has to have factors which are S minus A, S minus B, S minus C, because it has to be 0 if any of the lengths is equal to the semi-perimeter. It has to be dimensionally correct, so there has to be a fourth bracket. That fourth bracket has to be symmetric in A, B, and C, but the only sort of order 1 bracket that is symmetric in A, B, and C is A plus B plus C, and then we just need some constant. Okay, there was a request in the chat for, question 10. Right, I'm going to have a look at question 10. Where's problem 10? I need to make a judgment call of how much I can do in 6 minutes here. So find the equation of the circle passing through the origin, the point A10, and tangent to the circle x squared plus y squared equals 9. So x squared plus y squared equals 9 is a circle of radius 3. And this is the origin. Okay, the circle must be tangent to the circle x squared plus y squared equals 9, so must touch that circle and passes through the origin. Okay, so if I draw a common tangent to the two circles, the center of the smaller circle that I've drawn, so the inner circle, must lie on the line which is perpendicular to that tangent. But that line which is perpendicular to the tangent also goes through the origin. So the center of the small circle must lie on this line L1. So the center of C2 lies on L1. But that's important, because then that tells me that the origin and the point of contact, okay, so OT is the diameter of the circle. Okay, so I can give T a name. I can say that T, the point of contact, is 3 cos theta. Well, I'll call it 3 cos theta, 3 sine theta. Why not? So the center of the small circle is 3 cos theta over 2, 3 sine theta over 2. And the radius is 3 over 2. Okay, so all I need now is what I can do now is write down the equation of the circle. So it's x minus 3, and I'll just write c for cos theta, plus y minus 3s for sine theta over 2 squared, and that is equal to the radius squared, which is 9/4. Okay, I know it passes through 1, 0. So I get 1 minus 3c over 2 all squared plus 3s over 2 all squared is equal to 9/4. So now I get 1 minus 3c plus 9c squared over 4 plus 9s squared over 4 is equal to 9/4. But because c squared plus s squared is equal to 1, this term here is 9/4, so it cancels with the 9/4 here. So I just get that 3c is equal to 1, so c is equal to 1/3, and then s presumably is, I can then get s by Pythagoras. So s is the square root of 1 minus 1/3, so that's root 8 over 3, or plus or minus root 8 over 3. So that's 2 root plus or minus 2 root 2 over 3. So the center of the circle is 1/3 2 root 2 over 3, or 1/3 minus 2 root 2 over 3. Okay, and all I've done there is I've chosen an angle which is such that the point 1, 0 lies on the circle. Actually, I could do a little bit better because I know the radius of the circle is 3/2. I've got 3/2 here. This point here is 1, 0. So then I could just use I could have just used Pythagoras more simply, because if I call the center of the inner circle C dash, I've got this isosceles triangle O C dash A. This length is 1, this length is 3/2. So I can just find the coordinates of the center using Pythagoras. Okay. No, I'm just trying to work out why the x coordinate of the center is not a half. Oh yes, it is. Yeah, because the cosine is 1/3, so the center of the circle is 3/2 times 1/3, which is a half. Yeah, and that would have been oops. So I could have avoided this. I could have avoided this calculation entirely by this picture here. Okay, so this picture here tells me that my inner circle has got radius 3/2. It goes through the point 0, 0, and 1, 0. So the center of the circle lies on the mid. If I drop a perpendicular, it lies on the midpoint between 0, 0, and 1, 0, and then I can get the y coordinate by Pythagoras. Okay, that finishes the webinar. Does anybody have any questions? Cool. We'll finish the webinar there. I hope you enjoyed it. Thank you, everybody. Okay, I'm just going to end the meeting for all. I'm not sure if Vlad is there, but I hope your packing goes well, and I'll see all of you again soon. Bye-bye.